Okay, thank you very much. Thanks to Dan in particular for the chance to speak here. Okay, so that's the title of my talk. I'm going to be talking about spectral theory, in particularly the context of Subramanian geometry. So let me first maybe begin by explaining what is Subramanian geometry to begin with. So Riemannian geometry, everybody knows what it is. It's studying metrics on the tangent space of a manifold. But what the word sub means in Subramanian is that the metric is defined not on the full tangent space, but just on a subbundle of the tangent space. Okay, so this is the subbundle E, and the metric is just on E. And crucially, what will be assumed is that the subbundle satisfies what's called the bracket generating condition. So bracket generating means if you look at sections in E, they generate eventually all sections under the Lie bracket. So if you look at C infinity E, this generates all sections of all vector fields under the Lie bracket. Okay, and turns out this I will explain why this hypothesis is important, what it buys you. And it turns out under this hypothesis you can do a lot of geometry, just like Riemannian geometry. But however, there are peculiar phenomena that arise. So there's a weird dimension called the Hausdorff dimension, which comes up. And there's weird kinds of geodesics called abnormal geodesics, which also arise. And I will explain both of these phenomena as I move along here. And this is a really big subject. A lot of people work on this. There's a big community of people who works on this. And I myself got into it only a couple of years ago. I was led into it. I will explain how. And but however, there are by now textbook references on the subject. Maybe the first book on the subject was one by Richard Montgomery. This is a nice book. There's an article of Gromov. So this is not really a book, but it's kind of very big. It's almost like a book. And then there's also a new book by Agrachev, Bartolari, and Boskine just out this year. It's also something I would recommend. Okay, so let's, since we're studying bracket generating distributions, let's first begin with some examples of bracket generating distributions. So the first example is what's called the contact hyperplane. So you're just looking at a kernel of a one form, alpha. Alpha satisfies the contact condition. And under this, you have the Darboux theorem. So your contact hyperplane is spanned by these vector fields in some coordinates. And there's a missing dz direction, but that's generated just by the first brackets. Okay, so that's bracket generating. Now we have the analog. There's an even dimensional analog of the contact case, which is called the quasi-contact, or sometimes the even contact manifold. So this is an even dimensional manifold X. It's even dimensions. The hyperplane is again the kernel of a one form, nowhere vanishing. And now the d alpha restricted to the kernel of alpha cannot be symplectic because it's restricting to odd dimensional manifold, odd dimensional subbundle. But we can still insist that it has maximal rank. Okay, so it has a one-dimensional kernel. And in this case, we have what's called a quasi-contact structure. There is again a normal form, a Darboux normal form. This is a normal form for the kernel of alpha. There should be a functional multiple here. It's only a normal form for the kernel of alpha, and it looks more or less the same, except there is an extra coordinate w, and this dw appears in the span. Okay. And however, the bracket generation is again the same. dz is missing, but you can generate it by the first bracket. Okay. Now there's another kind of variation of the contact case, which is what's called the Martini case. So this is specifically a three-dimensional phenomenon. And in this case, you're again looking at a two-plane inside a three-manifold. It's the kernel of a nowhere vanishing one form, but it's not contact. So the contact condition can fail. So alpha wedge d alpha can be 0, but however it fails nicely. It fails transversely. Okay, so if you look with respect to a volume form, alpha wedge d alpha is a function. If you take its Radon-Nikodym derivative with respect to a volume form, it's a function f, and what we insist that whenever f is 0, df is non-vanishing. Okay, so then it's vanishing transversely in that sense, and in this case, away from the contact, away from this vanishing locus, it's there's still the Darboux theorem, and you have generation. But on the vanishing surface, the normal form changes a bit. It's spanned by, in the contact case, you have dy, and then you have dx plus y dz, but now on the vanishing surface, you start getting a y squared. Okay? But however, even with this y squared, still you can still check that it's bracket generating. So if the first bracket, you have a y dz that's still not generating the missing direction along y equals 0, but you can generate it by the second bracket. Okay? You can just take one more bracket to get rid of that y. Okay? So it's still bracket generating, this Martini case, and this is somehow, it will play a fundamental role later, this example. Another example is now also growing in interest among the topology community. So it's what's called the angle case. So now we look at rank 2, co-rank 2 distribution. Okay, so you look at, and the smallest dimension in which this can happen is the 2-plane inside a 4 manifold. And if we also insist that it's be structurally stable. So locally, if you perturb this structure, it should be diffeomorphic to it. Then there is again a unique normal form. Okay, so there is in some coordinates, this structure is spanned by these by 2 vector fields, which look like this in some coordinates. And you can just check that this is also bracket generating. So you need 2 steps. You need 2 brackets again to generate all the directions. Okay.
The angle case can make sense in higher dimensions too, right? Is it just a 4-dimensional?
Yeah, it depends how you define it. So the stability phenomenon, there's not so many. There's 4 or 5 bracket generating distributions which are stable in this sense, and I think this is in that sense, it's particularly 4-dimensional. Yeah, right. And however, here you saw this is co-rank 2 structure. You can have actually arbitrarily high co-rank. These are what are called Gulzar distributions, and there's some general definition of these I don't want to give you, but the point of this example is that it can be very high co-rank. You can have just a rank 2 plane inside an n manifold which generates the whole tangent space. Okay, so this is an example of 2 vector fields. And you can check this is increasing order x2, x3, x4, and then the dxi's are also increasing order. And each successive bracket generates the successive directions. Okay. However, in this case, you start getting, this is not a unique normal form. You start getting a whole lot of them. You start getting a moduli of these normal structures. And this is just the beginning. This is a really wild world of bracket generating. This may be too general, this bracket generating condition. This is too many types of distributions. It's already interesting to study the topology of these distributions and so on before putting a metric on them. So this is a really big subject. As you can see, it's going to be almost a huge subject, too big to study maybe. But let's see what we can do, some generalities. So since we have a bracket generating distribution, we can define what's called the canonical flex. So, we saw that the number of steps that we need to generate can be pretty high. So you can define the step size, the number of brackets that you need to generate eventually the full tangent space. And just to note that this can depend on the point. Okay, so as we saw in the Martini case, if you were in the contact region, you just needed 1 bracket, but you were in the vanishing locus of the alpha wedge d alpha, you needed 2 brackets. So this step size can depend on the point on the manifold. So it's in general, this is not a flag of vector bundles. It's only a flag of vector spaces at each point. But you can still keep track of the dimensions of this canonical flag, and you get a growth vector. Okay, so this growth vector is just keeping track of dimensions in this flag. And in the case when you actually do have a flag of vector bundles. So this that is the growth vector does not change. It's constant with the point. We have what you call an equiregular structure. It's just the definition. And in this case, a lot of the analysis will work out well. So it's a good definition to make. Okay, so that's just the definition. Now, what is the significance? Now, we explain the significance of the bracket generating condition. This comes in through an old theorem of Chow and Reshevsky. So what this theorem is saying is that if you have a bracket generating distribution, we can connect any 2 points. So eventually we want to do geometry. We want to define lengths of curves in your manifold. But since the metric is only on the subbundle, we can only define lengths of horizontal curves. So curves which move the direction vector points in the direction of the distribution. So we got to be able to connect 2 points by a horizontal path like this. And this is what this theorem is saying. So if it's bracket generating, we can connect any 2 points by horizontal path. And if you think about it, this theorem is in some sense the exact opposite of what's the Frobenius theorem in differential geometry. So in the Frobenius theorem, you have what's called an integrable distribution. So it's the brackets stay inside the distribution, and in that case you have a foliation. And if you have 2 points on 2 different leaves of the foliation, there's no way you can connect them. So it's in some sense exact opposite of that. Okay. And the idea behind the proof of this theorem is just a small calculation. So it's if you look at if x and y are 2 directions that lie inside the distribution, you can flow along x or you can flow along y, and then you can combine the flows this way. Okay, and these flows don't commute. The non-commutativity is measured by the Lie bracket. So to leading order, this combination of the flows is just flowing you along the forbidden direction of the Lie bracket. Okay, so this, even though you cannot move along you can combine the flows to move along, effectively move along the direction of the Lie bracket. Okay, so that's the idea behind the proof. And as we said, what it buys you, this theorem buys you a structure of a metric space. So now you can define a length of horizontal paths, and you can define a distance on your manifold just by the usual distance, infimum of lengths of horizontal curves connecting them. Okay, so now you have a metric space. You have now metric balls inside of your metric space. You can look at the volume of a ball with respect to some arbitrary volume form, and you can look at how fast this volume goes to 0, or at what rate the volume goes to 0 as the radius goes to 0. Okay, so this epsilon is the radius of a ball centered at the point x. At what rate does this volume go to 0 as epsilon goes to 0? That's just the definition of the rate. And in Riemannian geometry, this would be the dimension. Okay, the volume of the epsilon ball would go like epsilon to the n. But what's weird, this is the first weird phenomenon in sub-Riemannian geometry, is that this rate is now different. Okay, this rate is is going to 0 at a different rate. It's what's called the Hausdorff dimension of the manifold. And this dimension, this Hausdorff dimension, is strictly bigger than the topological dimension. Okay, so the balls are somehow bigger in this case. However, this Hausdorff dimension can be written in terms of this growth vector. So there's a formula for it, and this is what's called the ball-box theorem in sub-Riemannian geometry. Okay. Okay, so to understand why this happens, let's look at again. You have to go back to this formula. Now, in this formula, what you see is while these flows that on the left-hand side, they're at a scale time t, the flow along the Lie bracket direction, this combination is of order t. The time scale is time t squared. Okay, so we are moving slower, even though we are moving effectively in the forbidden directions. We're moving slower in those directions. And then if you want to move along a direction of the third brackets, you would move at order time t cubed, and so on. Okay, so each direction you can move along any of these directions, but there is some weight along at which you move, and the weight of a particular direction has to do with the position of that direction in this flag. Okay, and what the Hausdorff dimension is eventually the sum of those weights. Okay, so it's and the weights of the forbidden directions are bigger than 1, so that's why the Hausdorff dimension is bigger than n eventually.
But it is always an integer.
Yeah, it's always an integer by this formula. Yeah. Right. And in fact, you can also draw a picture of one of these metric balls. And this is a picture of the Heisenberg group, which is a contact three manifold. Okay, you can write it down explicitly, and x and y correspond to the allowed directions, and the forbidden direction, you see there's it's like the square. It's comparable to the square, and this is a metric ball is roughly something which looks like that, and it's not exactly a ball, even though it's called a metric ball. It looks more like an apple. Okay, okay, so the balls look different. So that's the first weird phenomenon. Now, another feature in sub-Riemannian geometry, this is a problem in sub-Riemannian geometry, is defining a canonically a volume form on the sub-Riemannian manifold from the sub-Riemannian structure. So now, since you don't have a full orthonormal frame of the cotangent bundle, you cannot just wedge things together to define a volume form. And it's not clear in general. This is a well-known problem in sub-Riemannian geometry, defining canonically a volume form. But however, in the equiregular case, when this canonical flag is a flag of vector bundles, there is a beautiful answer to this problem, which was given by Octavian Popp, who unfortunately he left math soon after graduation, but never published actually this result, this construction, but appeared later in Montgomery's book again. So the way the construction goes is you have your sub-bundle, you have the bracketing map. Okay, so the obvious map, which takes, if you have a tuple, so E1, E2, Ej is a bunch of vectors in your sub-bundle. You can define vector field extensions and take brackets the obvious way. You land in the span of the jth brackets. However, to define a tensorial map, you have to make it land in the quotient, otherwise it's not a tensorial object. So you have a natural surjective map on the bracketing map from the jth tensor power of E to this quotient and then the canonical flag. Okay, and it's surjective, so you can push forward the metric, the tensor product metric, to a metric on this. This defines a metric here, defines a canonical volume element here, metric volume element. And then eventually what you use to get a volume element on the tangent space is use this canonical identification of determinant lines from the flag. Okay. Okay, so this last element of the flag is the tangent space, and there's this canonical identification, right? So that's a beautiful construction. However, it only works in the equiregular case. The construction gives you something in general, but if the dimensions of these vector bundles are jumping around, it's not a smooth construction. Okay, so it's not a smooth volume form in general. Okay. So the problem of defining a smooth volume form is still open in general. Okay, so this is another nice problem in this field. Okay.
Your equation for Hausdorff dimension is just defined in terms of the non-smooth volume form, I guess?
Yeah, so it's defined in terms of an arbitrary volume form. Yeah, this volume here is, you can take any arbitrary volume form, and this rate doesn't depend on the choice. Yeah, the volume will depend. Yeah. Here you choose an auxiliary one, but the rate doesn't depend on it. Yeah. All right. Okay, so that was the first weird thing in sub-Riemannian geometry. Now, to explain the phenomenon of abnormal geodesics, let's first define what a geodesic is. Just a distance minimizer. You have a distance. There is an analog of what's called the Hopf-Renault theorem in Riemannian geometry. So it says that if you have, with your sub-Riemannian distance, if you have a complete metric space, then your space is also geodesically complete. So you can connect any 2 points by a minimizer. Okay. and you have these geodesics. You can find one class of geodesics just by Hamilton flow. Okay, so there's a natural Hamiltonian that's defined on the cotangent bundle. So C is a covector. You can restrict it to E to get an element of E dual. E dual has a dual metric, so you can take its norm square. So you get a function on the cotangent space. Okay, just this usual construction. And this has a Hamilton flow. It has Hamilton trajectories. You can project them. It's a theorem that these are always horizontal. That's easy. And moreover, they project to minimizers. Okay, so these short curves of these Hamilton trajectories are minimizers. But what's different in sub-Riemannian geometry is that it's not all of them. Okay, so you don't get all minimizers this way. And this was a topic of debate sometime in the 80s. It's actually in this book of Bismuth, he already says very clearly that not everything is a projection. So it's, but there was still some debate. However, in around 91, in the early 90s, Richard Montgomery, which found a very simple, beautiful example of an abnormal minimizer, which settled the debate, I guess. And this is an abnormal way to spell the word abnormal, but anyway, I'm sorry. It's not only did I misspell it, I highlighted the misspelling. So anyway, he found an abnormal minimizer, and the example that he gave was the Martini case that we just mentioned. Okay, so just looking at it locally. This was the kernel of this one form, which is not contact. The contact condition fails along y equals 0. And in this manifold, we can define a curve which is just the x-axis. So it's moving along the x-axis. And what is the significance of the x-axis in this case is that you can look at your Martini form. You can restrict it to the vanishing surface, and you can look at it has a one-dimensional kernel restricted to the surface, and that one-dimensional kernel is what's significant here. That corresponds to the x-axis, so it's moving along this kernel. And that's the abnormal minimizer, but of course I didn't tell you should object, because I didn't tell you what metric this is minimizing for. I just told you a distribution and a curve, and the surprising answer to that is that it actually doesn't matter. Yeah. So it's, yeah.
Sorry, can I pause you and go back to the previous,
sure.
previous slide? So if we're just on regular contact R3,
Yeah.
that's metric complete, or am I wrong?
Metric complete. Sorry, what do you mean?
Yeah.
It's metric. Yeah.
So I can't think of what a geodesic would be like, connecting 2 points that are, say, on the z-axis.
Yeah. There's pictures of this. I can show you later.
I mean,
Yeah.
I can see horizontal curves connecting them, but which is like the minimum? Like I don't see a.
Yeah. I think we have to. I have to show you some pictures. It looks a little weird, but it's some sort of spiral, I guess. Yeah, but I don't know. I can show. Yeah. It's smooth. Yeah. It's smooth. Yeah. There's a smooth minimizer. Yeah. I will mention. There's actually a question about these. I will mention it to you in a minute.
Okay.
Yeah, but I can show you some pictures. There's actually some nice.
What's the radius of the spiral? Maybe.
I don't know.
Okay.
I have to.
Anyway,
Yeah. Sorry. But they're really beautiful pictures of these, and even in the Heisenberg plane, for example. Yeah. We can look at them later. Okay, so where was I? Okay. Yeah, okay, so here I was, so I was, so I mentioned this curve in this Martini plane, but I didn't tell you, I said it was an abnormal geodesic, but of course I didn't tell you what metric this was minimizing for, okay, so it's, and you should have objected, but the surprising answer to that question is that it actually doesn't matter, okay, so it minimizes regardless of the metric. So to be more precise, the more precise statement of that is, regardless of what metric you put on your Martini plane, there is a sufficiently short arc of this curve which is minimizing between its endpoints. Okay? So how short depends on the metric, but nonetheless it's an arc of this curve. Okay? Okay, and indeed you should ask yourself, how can this thing be minimizing without solving a variational equation? So as if you write down a variational equation, shouldn't it be some sort of Hamiltonian condition? And the answer to that is it's actually, this curve is C1 isolated among horizontal curves. So in other words, there are no horizontal variations of this curve. Okay? So it's hard to write down a variational equation if you cannot find a variation. And this can happen. The topology of horizontal curves, the horizontal path space can have isolated points like this, okay, which is unlike the topology of usual curves, the usual path space. Okay.
So what you said, Boot had already said there are abnormal.
Yeah.
He didn't give an example of one, or did and nobody paid attention?
Yeah, actually, he does have an example. His example was different from this one, but there is an example. People kind of ignored it. I'm not sure. But this Montgomery not only gave this beautiful example, he explained many features of this example, like this isolated structure of the path space and so on. Okay.
So this Moot's example is not like that. It doesn't.
No, his example was some kind of Lie group. I mean, it's what's called a Carnot group. Yeah. But he didn't explain this topological nature of this phenomenon. Yeah. And Montgomery also pointed out the mistakes in some of the earlier papers, which showed that there weren't any. Okay. Anyway, so that's an example of an abnormal curve, but however, in general, we lack an understanding of these abnormals. And in fact, it's an open question whether these abnormals are always smooth curves. So it's conjectured they're always smooth. But since we don't understand them, we cannot say that they are, and this is a big open problem in the field. But however, they are well understood in some simple cases. The Martini case I already mentioned. In the contact case, there's some characterization which excludes them. And in the quasi-contact case, they correspond to the integral curves of the characteristic line. So characteristic line is remember d alpha, which restricted the kernel of alpha could not have been symplectic. That was because of odd dimensionality. There was a one-dimensional kernel, and that kernel generates these integral curves which correspond to abnormals. Okay, so this is a very nice story. There's many questions about dynamics in this Subramanian geometry, but unfortunately, I'm not actually a dynamical systems and topology person. So I'm more on the spectral theory and micro-local analysis side. So maybe I'm gonna switch to that. So maybe I disappoint you a little bit. But what spectral theory corresponds to is the quantum dynamics. So it's somehow what I'm going to tell you now is an effort to quantize this whole story. Okay, so that's what I'll do. And to describe quantum mechanics is described by Laplacians and Schrödinger operators in their spectral theory. So we have to define a Laplacian in this context. Okay, and there is a Laplacian that one can naturally define on a Subramanian manifold. So it's defined as follows. It's the usual definition. You just take divergence of a gradient. Okay, so a gradient combined with its adjoint. The gradient can be defined as usual. So you just gradient paired with a vector in your distribution is just directional derivative along the vector. Okay? So that's the usual definition. However, to define the adjoint of a gradient, the adjoint requires an L2 inner product. The L2 inner product is taken with respect to a volume form. So you need a volume form. Okay, and this, of course, was our conundrum from a few slides ago: how to define the volume form. But what we'll do now is just choose an auxiliary one. Okay, so it turns out that a lot of the spectral theory doesn't depend on this choice of the volume form. So you can just choose an auxiliary one and define a Laplacian that way. Okay. In some cases, you don't have to choose. You can use Pop's volume, for example, in the equiregular case, and define canonically a Laplacian. But for now, we just choose an auxiliary volume form, get a Laplacian. This Laplacian, it only differentiates in directions of the distribution. Okay, so if you look at it in local coordinates, what this does is this Laplacian that I just defined, it's a sum of squares of vector fields. This is the basis of your distribution, and then some lower order terms. Okay, so it's only differentiating in directions of the distribution. Okay, so it's missing a lot of directions, all the directions complementary to your distribution. So it's in particular, it's not elliptic operator. Okay, so it has a characteristic variety. The principal symbol of this Laplacian, it vanishes along some subset of this cotangent bundle. And that vanishing locus is exactly the annihilator of your distribution. Okay.
So the lower order terms, can those be in an arbitrary direction, or do those also have to be?
Yeah, they can be arbitrary direction, but they're lower order, so they're first order or less. Okay. Yeah, that's right. So, but however, even though it's not elliptic, it's missing these directions. What's the theorem here, and this is the significance of the bracket generating distribution condition from the quantum perspective, the spectral perspective, is through a theorem of Homander. So it says that if the distribution is bracket generating, then the Laplacian is what's called hypoelliptic. So what it means is that it satisfies elliptic regularity and all the analytic properties of an elliptic operator without actually being elliptic. Yeah. So it has a elliptic regularity property. Not only that, it also satisfies an analog of the elliptic estimate. So this is the sub-elliptic estimate. So it's in the usual elliptic estimate, you would gain two derivatives here, since it's a second order operator. But in the hypoelliptic case, you gain 1 over r derivative. So r is the maximum number of brackets that one needs to generate the tangent space. Okay. And the suboptimal this not only is this a sub-elliptic, its estimate is actually sharp. Okay, so this is the one. This is the maximum gain in regularity that one can expect under this condition. And this was proved by Rothschild and Stein a while back. So once you have a sub-elliptic estimate like this, you have a compact resolvent for your Laplacian. Okay, and you have a nice discrete spectrum of eigenvalues going to infinity. And we can start doing spectral theory. Okay, so you can start asking the usual questions about Weyls' law, how fast the number of eigenvalues less than lambda goes to infinity. You can ask for trace formulas, the wave trace formula. You can ask for propagation of singularities, quantum ergodicity, and everything. Okay, so there are very classical results about spectral theory in the Riemannian case, and we want to explore the sub-Riemannian analogs. Okay, so let's see what is known, and it turns out a lot of these questions are actually open in the Subramanian context. Okay, so it's very little known, and let me describe to you some of the things that are known now. So to see the Weyls law, the Weyls law, you usually use the heat Conal expansions. Okay, so the heat this e to the minus t delta, this is the evolution operator which solves the heat equation. You can look at its Schwarz-Conal, and you can look at it on diagonal. Okay, so this is the Schwarz-Conal on diagonal, and this thing has an expansion as t goes to 0. This thing has an expansion even in the Subramanian case. So this expansion starts now at t to the minus q. Okay, so this q is now the Hausdorff dimension, okay, and this was changing as we saw earlier. This can change from point to point, okay, So that's the weird thing about this heat Coulomb expansion in the Subramanian case, is that there is an expansion, however, not just the leading coefficient, the leading order even in the expansion. It changes from point to point, which is a really weird thing. And in particular, this expansion, you can see that this expansion is not going to be uniform. Okay, it's not the uniform in the point on the diagonal. Okay, it can't be. Okay. So if it's not a uniform expansion, you cannot just integrate this expansion to get a trace asymptotic. So the heat asymptotics of the heat trace, which is the sum of e to the minus t lambda j over all the eigenvalues, this expansion is not clear from this heat column. Okay. But however, in the equiregular case, when this growth vector and the Hausdorff dimension that doesn't change from point to point, everything is nice, everything is locally constant, and we do get a heat trace expansion and a corresponding Weil law. Okay, so this is the Weil law in the equiregular case, where this q doesn't change from point to point, and indeed that's what appears here. Okay. So two things. So one is that remember this q was much bigger. It's bigger than the topological dimension. So it's you see that in the hypoelliptic for hypoelliptic operators such as the Subramanian Laplacian, there's many more eigenvalues. Okay, so you have more eigenvalues than an elliptic operator, and the Weil law goes to infinity at a faster rate. And and the other thing is in the case when you do not have an equiregular structure, this q can change from point to point. For example, in the Martini case, this q can be, if you're in the contact region, this q is 4, or on the Martini surface it's 5. So it's not clear whether what appears in this Weil law is 4 halves or 5 halves. So it's not clear if it's 2 or 5 halves. And this is the subject of ongoing work to explore the Weil law in singular cases. What you see in the Martini case is neither 2 nor 5 halves, but somewhere in the middle. Okay, so you get a factor of a log. Okay, and so this team of three, Cologne, Hilaire, Trela, they're exploring the Weil law again in the singular case, and this is, in general, it's still open. Okay.
It's closer to 2 than it is to...
Yeah, it's closer to 2.
Does that reflect?
It reflects maybe the contact region being bigger than the vanishing locus. Yeah, I think that's what. Yeah.
Does C somehow depend on the size of the vanishing locus?
Yeah. C is given as an integral over the vanishing locus. Yeah.
Okay.
So this integral somehow, the integral of the heat cone, it concentrates along the vanishing locus. Yeah. Right. Yeah. So that's the first result. Already you see that the leading term in the Weil law sees this exotic Hausdorff dimension. Okay. And now the second question was to one could ask is whether does the spectrum of the Laplacians see this abnormal geodesics. Okay, so that's the second kind of weird phenomenon in Subramanian geometry. And to see geodesics or dynamics in the spectral theory, usually you look at not the heat equation but the wave equation. Okay, so let's analyze now the wave equation. The wave equation is much harder to analyze. You have to use this half wave operator. So this solves the half wave equation. If you square it, you get the full wave equation, and you have to analyze the trace of this. The trace is not a function. The sum of complex exponentials. This is this trace. It's not a convergent in any way. It doesn't give a function, but you can make sense of it as a distribution, as a generalized function, and in time. And this has singularities. Okay, so since it's a distribution. You can look at singular support of this distribution, and this was in the Riemannian case. This was done by Doistermaat and Guillemin. This is a classical result. In the Riemannian case, the result of Doistermaat, Guillemin, and Chazeran, it says that the singular support of this wave trace is contained in the length spectrum, okay, so the geodesic length spectrum of your manifold. Okay. And in the hypoelliptic context, there was a generalization of there was a corresponding result proved by Melrose about 35 years ago, and he analyzed effectively what's the three-dimensional contact case of the Subramanian Laplacian. Okay. And in this context, he was able to prove the Poisson relation, like the Dostermaat-Gilliman Poisson relation in this case, and correspondingly the Sharp-Weil law. So to prove the remainder in the Sharp-Weil law, you need to analyze the wave trace like that. Okay. And this analysis was quite difficult. It only worked in the three-dimensional contact case. And recently, again in the three-dimensional contact case, the same team of Cologne, De Verde, Hilaire, Trela, they were able to prove quantum ergodicity. Okay? Quantum ergodicity on a three-dimensional contact manifold. So quantum ergodicity, what it means is that if you look at not the eigenfunctions, not the eigenvalues, but the eigenfunctions of your Laplacian, they should get equidistributed on your manifold. Okay? So if you take norm square of the eigenfunction, they should get equidistributed, and to achieve equidistribution like that, you need a hypothesis on the classical dynamics on your manifold. And this team was able to show that the correct hypothesis on classical dynamics in this case is the Rabe dynamics. Okay, so this was the first appearance of Rabe dynamics in on a base manifold in the sub-Riemannian geometry.
Like generically, can one hope for quantum ergodicity? I mean, if you don't know that the rate flow is ergodic.
Yes, I think. Right.
Well, you might have some invariant tori
Yeah.
in certain situations, and
Mhm.
you can't get rid of them. That separates us.
Right. So is generically the ray flow ergodic? Maybe. I'm not sure.
Well, that wasn't quite what I was asking.
That was what you were asking?
No.
What were you asking?
I was asking, could you hope that in some generic sense you have quantum ergodicity? I mean, so if generically the rate flow is ergodic, then you could just use the theorem.
Yeah, right.
In general, maybe you could hope that generically use quantum ergodicity, but I don't know.
Yeah, I think whether the ray flow is generically ergodic, I'm not sure, but maybe this is a. Yeah. It's not. Oh, okay. Yeah, I don't know. This might be a good question. I don't know. Yeah. But yeah, anyway.
Ask Peter.
Yeah. All right.
I mean, in the standard case, he has thought a lot about it in arithmetic models. So.
Yeah.
But not necessarily about that thing, but would be good to know what one can expect in the more classical situation.
Yeah. Yeah. Anyway. Yeah, but anyway, this was one appearance of the Rabe flow in spectral theory, actually around the same time as this thing. Their preprint appeared in the archive. There was a preprint of mine, but I studied not the Subramanian Laplacian, but its semi-classical analog, and this was the magnetic Dirac operator. This square, its square of this is morally a Laplacian, and it's, of course, this is interesting for spectral theories, but I also had another motivation for this problem, which was coming from Taubes' proof of the Weinstein conjecture. So there was some spectral component in that proof, and this is the reason I was studying this, and this is how I got into the subject, actually. After somebody pointed out their work to me, and I contacted them to understand the relation, and this is when I realized that this fit into a much more general framework of Subramanian geometry, what I was doing. Yeah. Okay, anyway, and however, in this contact case, there are no abnormal geodesics. So, and these results somehow confirm the fact that you don't see any weird thing on the right-hand side here. It confirms that there is no mischief going on in the wave trace. So, the natural thing to look at would be the quasi-contact case, where there are some abnormal geodesics, and this is what I analyzed recently. So I proved the analog of the Dostermaat-Gilliman trace formula in the quasi-contact case, And again, you see a similar Poisson relation, except that you see what this T abnormal is, it's the length of the shortest characteristic curve, closed characteristic. Okay. And what you see here on the right-hand side is, actually, this is a very big interval. This is almost it's maybe saying nothing at all beyond this time. And there is a reason for it, but at least within this range, you can see that there are no abnormals. So in some sense, it's telling you that abnormals are significant. But the reason for this big interval is what can happen is if you take any length in here, in this big interval, what can happen, you have a sequence of normal trajectories whose lengths are converging to that given length in that interval. Okay. So this set can actually be dense inside this set. Okay. And this can happen in examples. Okay. So this is really somehow in some sense optimal. And not only that, I was able to prove the sharp-Weyl law. I was able to prove a refinement of the Weyl law under the dynamical assumption, which is again on the closed integral curves of these characteristics. And this is again an analog of the remainder estimate of Doistemart and Gilliman in the Subramanian case. And there's also quantum ergodicity. So I was able to prove quantum ergodicity, where now the ergodicity hypothesis, instead of the ray flow, you look at the characteristic flow. Okay, so you look at the subsets which are ergodic, so which are invariant under the characteristics. So they're unions of closed characteristics, and if this characteristic flow is ergodic, then you have quantum ergodicity. Okay. In just a brief word on just a remark about the proof, really, it's in Riemannian geometry, what you use to prove such wave trace formulas is the pseudo-differential calculus, the pseudo-differential and Fourier integral calculus of Homander and Doistemart. But in the Subramanian case, it doesn't quite work. In particular, the square root, if you take the square root of the Laplacian, it's not a pseudo-differential operator anymore. And you have to use an exotic pseudo-differential calculus. So you have to construct a new pseudo-differential class, and you have to show in which your square root lies. Okay, so much of the paper is just constructing the pseudo-differential calculus and showing its properties. Okay. Okay, so that's what I wanted to say about the spectral results in Subramanian geometry. So in the time remaining, I want to say something related, which is an application to complex geometry. But maybe I pause for a minute to ask for questions before I switch a little bit. Yeah.
So what about in some other Subramanian cases? I mean, you said there's a lot of cases.
Yeah.
Can one expect a similar story for?
Yeah. So as you see, there's it's a wide open field right now. So there's many other cases you can analyze. So what I would have liked to do really was this Martini case, for example, which there's this nice description of all the abnormals in this. It's very well understood, the dynamics. But however, the Laplacian turns out to be more difficult to analyze. So in this quasi-contact case, you get transversely to your characteristic variety, you get some sort of harmonic oscillator. In that case, you get it's more complicated. You get an anharmonic oscillator, and but
so
it's a problem. Yeah, it's a problem. Yeah.
And what about subleading asymptotics? I mean, are there no? I mean, so I see that you have some subleading asymptotics, but you said something about that being sharp, or
So this
is it possible to ever extract any coefficients?
So this thing is sharp. This thing is analogous to Doistemart-Gilliman. If you want a second term in this expansion, right. This is already difficult in Riemannian geometry, for example. There's nothing that's known. So it's So Doistemart-Gilliman somehow did the best in this context. There's even in Riemannian geometry, there's no second term in these Weyl laws.
Right.
Yeah, but maybe in Subramanian might be different. I'm not sure.
Right.
Was that your question?
Yeah.
Yeah. So I don't know the answer to that.
Maybe in some special cases.
Yeah. All right. Any other questions?
Sorry, just to
Yeah.
double check, the LE is the kernel of.
Yeah. It's the kernel of d alpha restricted to the distribution. So it's the So it's not symplectic d alpha. The restriction of d alpha. So it has a. Yeah. And this is all in 4 dimensions, by the way. So it's also a problem to do it in higher dimensions, even dimensions. Yeah.
So
Yeah.
this may be a weird question
Yeah.
if you haven't thought about it before. So one particular instance would be like if it's an angle, if you have an angle structure,
Yeah.
the first bracket closure is
Yeah.
contact. Do you get any stronger results in that case?
Oh yeah, that's another situation I wanted to analyze is the angle case.
Okay.
And because in the angle case, it's also known that this Montgomery phenomenon. So it's that the characteristics are necessarily minimizers, and they're C1 isolated, and it's the same as the Martini example. So again, that's another example that I want to analyze maybe in the future. Yeah, the angle case. Yeah.
Okay. Because I mean, this case kind of, well, it's sort of, anyway, yeah, thank you.
Yeah. Okay. Yeah. No, there are many questions. Yeah, it's very interesting, I think. Yeah. Okay. So anyway, so in the last little time that I have, I want to explain a very nice, surprising connection we found with complex geometry. So, to explain the connection, what we started with is a natural, particular kind of Subramanian structure. So there's a natural place for Subramanian structures. And this is on circle bundles. So if you start with now a Riemannian manifold, and you start put on it a complex line bundle with a Hermitian metric and a compatible connection, you can take the unit circle. This is X is a unit circle, and on that there is a natural distribution, namely the horizontal distribution, that corresponds to the connection. Okay, and then there's a pullback metric on this can be pulled back from the base. So now the first question to ask is, when is this distribution bracket generating, right? So the answer is given by this following proposition. So the step size, the number of brackets that you need to generate, so there's only one missing direction here, the vertical direction. And if you think about it, it's given, the step size is given in terms of the curvature on the base manifold. So the step of E is -2 is the order of the vanishing of the curvature. Okay, and that's an easy. The first bracket gives the curvature. That's just the definition. If that vanishes, you keep taking brackets that corresponds to differentiating the curvature. Okay, and therefore it's bracket generating if and only if the curvature vanishes to finite order on the base. Okay, and there's a corresponding decomposition of your manifold depending on according to the order of vanishing of the curvature. Okay, so this Yj is the subset of your manifold Y where the curvature vanishes to order J. And this will play a role in the result. Now on the unit circle, you have your Subramanian Laplacian. Downstairs, so the unit circle carries a circle action, so there's Fourier modes to the circle action. So you can decompose this functions along by their Fourier modes. What you get is functions on, actually this should be a Y. So not functions on the base, the kth Fourier mode corresponds to sections of the nth tensor power of your line bundle on the base. Okay. Okay, and if you decompose your Laplacian by these Fourier modes, the kth Fourier mode is the Bachner Laplacian. So you have your connection on your base manifold. Its kth Fourier mode is the Bachner Laplacian. So you have the tensor product connection, you compose it with this adjoint. Okay, that's the Bachner Laplacian. And you can use the Subramanian heat kernel on upstairs, take its heat kernel expansion, and you can decompose it by its Fourier modes. Okay, and you get a new theorem about just by Fourier decomposition. You get a theorem about the Bachner Laplacian expansion of the Bachner Laplacian as this tensor power goes to infinity. Okay, this is the semi-classical expansion. And using this heat Cologne expansion, we were able to prove an asymptotics for the first eigenvalue. Marinescu and I, we found the leading asymptotic for the first eigenvalue of this Bachner Laplacian here. And not only that, we were able to show some concentration for the first eigenfunction. It concentrates on the locus where the curvature vanishes to highest order. And this actually generalizes, so Montgomery analyzed this problem in the Martini case. So this is the circle invariant Martini case. Okay? So that corresponds to looking at the circle bundle over a Riemann surface, so you get something three-dimensional. And following Montgomery, this sparked a lot of activity. There's a lot of people who followed up on it. But however, all of these papers, they seem to fail to realize that there is a Subramanian heat Cologne on the unit upstairs on the unit circle. They just work downstairs on the base manifold. And well, we kept track of that, and we got a full, very general result. So this was very nice. And finally, this is my last slide. So finally, if your manifold is not just a real Riemannian, but has also a complex structure, you can define not just the Bachner Laplacian, but the Kodara Laplacian. Okay, so this keeps track of the complex structure. It acts on sections of tensor power with values in forms. And you can look at the Bergmann, what's called the Bergmann kernel. So you can look at the harmonic sections which generate the cohomology. You can look at its normal basis, and you can take its norm square here. This Bergmann kernel is the Schwarz kernel of the projector. Okay, so it's projection there's a projection from smooth sections onto holomorphic ones. And the asymptotics of the Bergmann kernel, they play an important role in complex geometry and in the geometric quantization. And the Bergmann kernel is related to the kernel of this Kodara Laplacian. You can analyze the Bergmann kernel once you have a spectral gap in the Kodara Laplacian. So in the previous formula, you had a spectral asymptotics for the Bachner Laplacian. This is related to the Kodara Laplacian by the Lichnerwick's formula. And you can get a spectral gap, corresponding spectral gap in 2 dimensions for the Kodara Laplacian, assuming your bundle is semi-positive. And once you have a spectral gap, there is a whole theory of local index theory techniques by starting from Bismuth-Lebeau and then Dialu, Ma, and Marinescu, which gives the Bergmann kernel expansion, which we were able to exploit to give the Bergmann kernel expansion on a Riemann surface for a semi-positive line bundle. Okay, and this was new. This generalized. So Tian in his thesis back in the day analyzed the Bergmann leading term of the Bergmann kernel in the positive case. Catlin and Zeldich improved it to a full expansion. And this was the first case where somebody proved the expansion in a semi-positive case at the vanishing points for the curvature. Okay. And this was really motivated. This may be one of the successes of the Subramanian spectral program. This was really motivated by Subramanian geometry in the end. Okay, so that's it. Yeah, thank you.